Okay, Master Mason Note, George Scoville coming at you here. Figure we're doing up today. We've been dealing with the EPR paradox, been touching into a few different types of math. Right now I'm trying to take it on three brown, one blue, and I'm trying to integrate that. This is the stone mill version to n1/2 of the math. That's the computer engineering version of the n1/2. And they're both in a four-dimensional quadrant where I say stone mill, math, stone mill, X, Y, computer programming, because if this is electromagnetism, mathematics, in the form of gravity, this is the class. Then the weak force is essentially in the stone mill are all these rational numbers that have a physics, this process, air crane, reciprocals, all those points here on the little graph. Each one of those boxes is originally one of the quadrants. In math, here we say stone mill, everything from the top down. Whose deliberated jobs and tasks they are, because not only is there one line, there's multiple lines. About, I know when I was doing the 5-footers over the Delaware Basin, I could come in, and usually it was the same thing. Check the break room, come through, rollers, start walking through, and then the courses diverge. It has a turbulent flow. Now on the mainline gravity, what you do is you go over and check the tool shed. Make sure everything's where it's supposed to be, and that way. And if the floor was arrangement different before I had to walk into there, some irrational little number on why this went down and that went up on performance is electromagnetism, because essentially that's going to lens light, that's going to act as an accretion disk or an Epson sphere around that black hole, both the horizon problem, and I need to know what's going on in that accretion disk or Epson sphere to determine what the mass is. And again, that's not acting as a sun, that's acting as a quantum object, a really, really big one. Let's talk about Rich, Jordan, its position. Now, equally, we share zero mass. But right here, that's different. All right, so in the morning, you could hopefully see. Now, basically, we could just start writing equations back there. Here's a triangle that says whoever, Kurt, Trump, and then there's already an x squared or an ax squared situation. And basically they're parallels because this graph does the same thing for both of them. Now we're going to take ax plus bx and we're going to add it into ax plus bx and see what the causal number x that has an entropy of y in time at causal mathematical functions of space and scale. There's space and scale. Time would be a scale. Money would be a scalar, x, y, and z. If those numbers are correlated on the floor here, then they become that air acoustic flutter in the mill that says that tomb of the unknown mason right there. So bridging general relativity and special relativity, this is special relativity. All the states in here that are the mass gap is the laser beam or the orbitals of the experiment that shows during an eclipse the light around that black hole, or the moon, is much more intense because it all gets focused around that small matter of gravity, that irrational number, that x. When I parallel that system and say, all right, I'm looking at this move in front of whatever I determine to be that main flow, okay? And in there like that, hopefully you're going to be able to see like, oh, well, that is general. And mathematics is in general how you form that. But what you got to have down here on the floor is you can't have teachers saying stuff like the problem between the mass gap and conventional mathematics as a whole, that wave function symbols don't immediately teach you how to run this stone. I don't expect to jump into Fermilab and just have a full understanding of their machines. You would want some kind of timeline in gravity where I can do the calculus trial and error, or have somebody reference me on a test, -1, +1s, in that entropy of that state. Because I'm going to say entropy is not full to the skill sets here. Entropy is not full to, even though the skill sets are done, they're not all in the right place at the right time after the test. So that's how you become a little bit more apt in understanding, hey, this is Euler's number. Just some time dilating, time paradox, EPR paradox, that an arrow in this motion is going to have air friction, and that's going to make it wave. And these lines that are polarized and redshifted and whatever just have to know the internal physics to really be able to say, hey, I'm traveling around this galaxy, black hole, sun, star. And then instead of numbers like radiation, something like in this planet, there's asteroids or a moon that creates tides. Now, if you just autopilot that stuff, you got to have guys in there close enough, and then I'm entropy. I'm in the room, I don't know exactly what it is. That's the changeover, because that's what that number represents in this space. Now, hopefully you can see what I'm saying with big dog numbers. It's good to have that skill. It's good to be able to recite a half-hour video, write that all up on the whiteboard for the safety guys. But that's where you got to be able to provide that here, because I don't see the result mathematically. If kids are going to college, how come I don't hear a lot of this? I see a lot of math teachers opposing the model with good technique. AX, BX, write the whole thing out, Pythagorean theorem, do one on Schwarzschild's radiuses and things like that, but we're still in this process, running this rock, getting it to the table and out the door. Catch you on the next one.